Hi everyone, this is Mohammad Umar Nasir, and I will be presenting on Augmentative Topology Agents for Open-Ended Learning. I thank my colleagues Michael Beckman, Dr. Stephen James, and Professor Christopher Cleghorn for their tremendous support. Um, we will look into a brief introduction to open-ended learning, then we will see what motivated our work, and then we dive into augmentative topology enhanced poet ATEP framework that we introduced, and then we will look into results and we'll finish off with conclusion and future works. So, what is open-ended learning? Um, it could be described as agents' behavior to progressively learn through divergence, in the sense that it evolves endlessly. As Professor Kenneth Stanley says, that if we come after a million years, we will find magnificent artifacts through these algorithms, and theoretically, it should produce that. So, current state of the art are paired open-ended Trailblazer, Enhanced Poet, Excel that takes on the adversary approach and is state of the art of that domain, and Xland and MindDojo produces large number of benchmarks for open-ended learning. So, what motivated our work? We have seen in the major works in open-ended learning that fixed topology leads to limitations in learning complex tasks, meaning that as tasks get uh, difficult, the fixed topology agent would stagnate and learn slowly. So, to the best of our knowledge, none of the previous works addresses this issue in open-ended framework, uh, and so we looked into the benefits of augmentative topology agents. Um, Two components that we believe that makes a truly open-ended learning algorithm are environments that can evolve endlessly and agents that can solve them endlessly. So both of them are equally important. So um, the next way we are going is augmentative topology enhanced poet, which we introduced, um, which is called ATEP. Two changes we made to EPOET for this. One, we used NEAT as the augmenting topology of agents algorithm, and in essence, any algorithm can be used. And the transfer mechanisms, fitness-based ATEP and species-based ATEP, which we'll go into right now. Fitness-based transfer FPT ATEP is inspired by EPOET's original transfer mechanism. Basically, does everything exactly, but with needs perspective. So we take the best genome, and we see that if it is better than all previous five uh, uh, generations best genomes of the target population, then we fine tune it, and then again we see that if it is still better than the best of the five previous best genomes of the target environment, then we transfer it such that we replace the whole population with the candidate population. The second that we introduced the transfer mechanism, which is a novel one, is species-based transfer (SPT ATIP). We take the best genome of the candidate population and find delta value. Delta value is the speciation that we have taken from NEAT, and we take the advantage of that, and and which is calculated by a linear formula, which then we see that all the target populations best genomes delta value should be within a threshold, which means that both of the best genomes, target and the candidate, are similar. Then we transfer the candidate species, only species, not the whole population, to replace the target species, and again not the whole population over here. So after this, we move on to results. The main result is to look into open-endedness, where we see the score, which is called accumulated new and novel environments created and solved, and annex, which says, right, it just it needs to create the environment, and the environment needs to be solved as well. Otherwise, it can create unsolvable environments. So, here we see that SPT ATEP performs the best, has a good difference between SPT ATEP and our first baseline. The second baseline is quite far away, and yes, to add over here, if we had a bigger controller, definitely it would have been performed better than SPT ATEP. But at some point of complexity, it would prove our hypothesis and become better than that controller. Um, and also considering that neat does not scale as much as it should, other algorithms will then come in handy if you are comparing a bigger size controller. So then we do some node exploration analysis. We say fitness to nodes ratio. Uh, uh, Larger the better, and species based transfer SPT8 holds for quite a bit, and then becomes almost like others. And then in annex to nodes ratio, we see that it has SPT8 has greater advantage over here. Then we come to accumulated nodes over time, and this is interesting because it only takes about as much as a smaller controller, but it performs really better, which is definitely an open question where why does it do it, and it is very interesting. And then we look into nodes to fitness mapping, and we see that SBT ATEP is uh, uh, as good as others, but with lesser nodes. So this is interesting as well. Then we look into generalization ability, where now we take 80 environments, self-created environments, and 80 agents of those environments. We sort out an emergence manner, and we now can observe that from left. The left is EPOET original controller one, then FPT ATEP, then SPT ATEP, and SPT ATEP does perform really well. At the later stages, the agents are performing very well. We want to decrease the green color over here. Then we second test, we take 20 environments of other algorithms, and we take for the algorithm that is being tested, we take the agent that is one of the latest agents that has solved the environments. And again, we see that SBT ATEP just crosses the mark from FPT and EPIT 40/40. And to conclude, we say that we have empirically showed that ATEP outperforms EPIT due to augmenting topology, and also due to better transfer mechanisms. It is more open-ended and generalized agents it produces. For the future work, we suggest to exploring ecology diversity. We suggest exploring more better transfer mechanisms and researching on more environments, as this was done on only 2D bipedal walker as a proof of concept, as EPIT was done. Thank you very much.